Okay, this is going to be our longest video, I think. But we want to talk about bits, bytes, and binary. So let's jump right in. I'm going to start off with a video from code.org to give you some background.
Hi, my name is Limor Freed, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary-looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only two options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8's position, and so on. For example, the number 9 in binary is 1, 0, 0, 1. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only ones and zeros, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. when you consider that a typical image has millions of these pixels. And a typical video shows 30 images per second. Now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Okay. So, just like you saw, it's a quick review. Computers contain these tiny switches on or off, right? And they're called transistors. Bits then is the language of computers. So is it a 1 and on, or a 0 and off? Okay, and so that's how all computers communicate. Now that becomes important to us in security because we can then take a look at these ones and zeros and we can actually read them. We can actually know what they mean as we're looking at different systems. Okay, so if you wanted to know, about how many bits are in each thing, got a few things here. That's a lot of bits for Microsoft Word. Okay, but we tend to group bits together, right? So if we have 8 bits, it's called a byte. And kind of cringy, but if you only have 4 bits, that's called a nibble, because a nibble is a little bit less than a byte. Yeah, I know, but that's actually important when we represent text with numbers in binary. Okay, so us humans, we don't use binary, we don't use these ones and zeros, right? But we code in different languages, and those programming languages are then converted into binary, which the computer understands, right? So we're going to dive a little bit deeper into the binary system because the more you know about this, the better your knowledge is, especially in the areas of networking. So when we talk about security and network and traffic and all the data that flows within our networks, these binary, and we'll talk later about hexadecimal, it's all really important because it makes up the data that we can then examine as we're dealing with incidents. So go ahead and take a look at this video.
Behold, the transistor, a tiny switch about the size of a virus that can control the flow of a small electrical current. It's one of the most important inventions ever, because when it's on, and when it's off, it's off. Sounds simple, probably too simple, but this either-or situation is incredibly useful because it's a binary system, on or off, yes or no, 1 or 0. With enough transistors working together, we can create limitless combinations of ons and offs, ones and zeros to make a code that can store and process just about any kind of information you can imagine. That's how your computer computes, and it's how you're watching me right now. It's all because those tiny transistors can be organized or integrated into integrated circuits, also known as microchips or microprocessors, which can orchestrate the operation of millions of transistors at once. And until pretty recently, the only limitation to how fast and smart our computers could get was how many transistors we could pack onto a microchip. To understand the device that you're using right now, as well as the challenges computer science is facing, and what the future of computing might look like, you have to start small. With that transistor. A transistor is essentially a little gate that can be opened or shut with electricity to control the flow of electrons between two channels made of silicon, which are separated by a little gap. They're made of silicon because silicon is a natural semiconductor. It can be modified to conduct electricity really well in some conditions or not at all in other conditions. The transistor has two modes, on and off. 1 and 0. All the information your computer is using right now is represented by sequences of open and shut transistors. So, how does a bunch of 1s and 0s turn into me talking to you on your screen right now? Let's just imagine 8 transistors hooked up together. I say 8 because 1 byte of information is made out of 8 bits. That's 8 on or off switches. That's the basic unit of a single piece of information inside your computer. Now, the total number of possible on-off configurations for those 8 transistors is 256. That means 256 combinations of 1s and 0s in that 8-bit sequence. So let's say our 8 transistor microchip is given this byte of data. That's the number 67 in binary, by the way. Okay, so what now? The cool thing about binary data is that the same string of 1s and 0s can mean totally different things depending on where it's sent. Different parts of your computer use different decoding keys to read the binary code. So if our teeny tiny little 8 transistor microchip kicks that byte over to our graphics card will interpret it as one of 256 colors, whichever one is coded as number 67. But if that same byte is sent over to our sound card, it might interpret it as one of 256 different spots mapped onto a sound wave. Each spot has its own sound, and our byte will code for a spot number 67, so your speaker will put out that sound. If it's sent over to the part of your computer that converts data into written language, called the UTF-8 code, it turns it into the letter C. Uppercase C, actually, not lowercase c, which is a different byte. So our 8 transistor processor already has a lot of options. The problem is that it can only manage 1 byte of data at a time, and even if it's flying through bytes at a rate of a few million per second, which your computer is doing right now, that's still a serious data checkpoint. So we need more transistors. And then more, and more, and more.
Okay. So we're converting binary into text, right? And so every time you text somebody on your phone or however you're doing it, you see a letter when you push the button or the key, and that letter is represented by a number. In this case, capital A is 65, and in binary, it would look like this. This system is called ASCII. And, it's American. It's an American system. I think the A stands for American. But this is how we represent letters using our binary 1s and 0s. If you take AP Computer Science, you will need to convert back and forth. And even in this class, you may need to convert between these different number systems, but we'll talk about that later. Okay, and so in our decimal number system, it's base 10. And that means we go from 0 to 9. And so in each place value, you can have just one number in each place value, and the number is 0 to 9. So once you want to pass 9, what do? You carry the 1 to the next place value, and then you reset that number back to 0, right? So you get 7, 8, 9, and then when you want 10, carry the 1, the 9 becomes a 0, and that's kind of how our decimal system works, right? And I explained that slowly because that's also how the binary system works. So you only have 1 and 0. So say you have 1 in the first place value. When you want to increase that, you need to carry the 1, and that first 1 becomes a 0. And so you have 1, then you have 1, 0. The next number is 1, 1. And the next number would be 1, 0, 0. Okay, so each time we're carrying the 1, and if we exceed the largest number possible, which is 1, then you have to carry it to the next place value. And that's kind of how we count in the binary system. All right? So this should be pretty self-explanatory to you. Every time you see the on of the light, it's a 1, and every time it's off, it's 0. Okay, and we do use 8 bits to form a byte. And so how do we convert from one to another? Pretty simple. We just multiply. So as we multiply, 64 times 1 is 64, 8 times 1 is 8, 4 times 1 is 4, 1 times 1 is 1, and multiply all that out. The zeros, of course, are just 0. And then we add them all up. And so this binary number, 01001101, is 77. Okay, here's another example. So multiply it out. 128 plus 4 plus 2 is 134. Okay, and once you start to get this, you can then explain this joke. I need to sign you off on my phys ed homework. This says you're supposed to do 100 sit-ups. You really did that many? I did 4. 4 isn't 100, Jason. Allow me to explain the concept of binary numbers. Allow me to explain the term fat chance. So if you understand binary, you get the joke. All right, I'll talk to you again in another video.